In this lecture, I will present two comparison-based sorting algorithms, Selection Sort and Insertion Sort. Their technique differs from each other and from the bubble sort, which was in previous lecture, but are pretty simple to understand and implement. In addition, I will show how shell sort is designed and how it performs. Actually, it is based on Insertion Sort and is an improved version of it. Let's start with Selection Sort and see how it works. We will also check how many comparisons and swaps each algorithm will make. Selection Sort is an algorithm that selects the smallest element from an unsorted list in each iteration and places that element at the beginning of that list. At the beginning of sorting, let's say that we have 7 numbers that are randomly distributed in the array and we want to arrange them in ascending order. Selection sort algorithm starts with the first element and compares it with the next element in the array. In this presentation, the smallest element is always marked in a red color. For better understanding, the compared element is marked in blue color. We go through the array, and if we find smaller element, we assign this element as minimum and mark it in red color. Here 8 is smaller than 32, so now the smallest element is 8. The process goes until the last element in the array is reached. In the first circle, the minimum element is found, that is 2, and it is swapped with the first unsorted element in the array. Then it is marked as sorted, green color. Now we repeat the same steps from the beginning of the unsorted array and swap the smallest element with the first element in the unsorted part. More and more elements become sorted and less iterations are needed in every circle. At the end of sorting, 21 comparisons were made and only 2 swaps. This algorithm has bad time complexity, and no matter how input data is distributed, the algorithm forces to make comparisons until the end of sorting, even though the array is already sorted. Space complexity is constant, but this algorithm is not stable. It is possible that the order of similar elements may change while swapping with the smallest element that was somewhere at the end of the given array. Now let's look at the implementation of selection sort. First, we assign n to be the length of array, then walk through array, and before every inner loop, the minimum element is assigned to be the first one in the unsorted part. We search for the smallest value comparing each element in the array. In this slide, the smallest element is pointed with purple arrow. Then first circle is finished, the smallest element is swapped with the first one in the unsorted part of array. We repeat the same steps until the length of unsorted part is equal to 0. Move on to the next sorting algorithm, that is insertion sort. This algorithm places the unsorted element at its suitable place in each iteration. Suppose we need to sort the array that is shown in the slide. At the beginning, the first element in the array is assumed to be sorted. Then the next element is compared with sorted one, and if it has smaller value, they are swapped. Right now, there are no more elements in the sorted part, so this element is marked as sorted. Now move to the next element. This time compared elements are in the right order, so no more comparisons are needed, and third element is marked as sorted. Move on to the next element of the given array and compare with the first one on the left side. If they are in reversed order, swap them. We repeat the same steps until all elements are marked as sorted. As you may notice, insertion sort made less comparisons than selection sort, but even 12 swaps instead of 2. Insertion sort still has bad time complexity, that is quadratic. However, this time the best case scenario is linear if array is already sorted. Space complexity is constant and the algorithm is stable. Equal elements do not swap. The implementation of insertion sort is still simple. For better understanding, in previous animation I showed that in every comparison elements are swapped if they are in reversed order. However, insertion sort is called insertion because it does not swap elements. It inserts element in the right position. They move through the array until the end, and before every inner loop they assigned temp variable to be the first unsorted element of the array. At the beginning it is 32. Then we define j to be the length of sorted part and go through all sorted elements, moving them to the right until the right position of temp variable is found. After that, we insert element in the right position. In the first circle we had only one element, so we don't need insertion. In the next iteration, element with value 8 is inserted in the right position. Repeat the same steps until the last element of array. Shell sort is more complex sorting algorithm that is based on insertion sort. It works on the same principle but compares elements with a gap. This time, let's take the array of 8 randomly distributed elements. Start comparing elements that are at a certain distance apart. At the beginning, the gap is equal to the length divided by 2. In our case, it is equal to 4. It is important to mark the end of sorted part. And remember, in every iteration, only elements with a certain gap are compared. In this slide, the end is marked with red color and compared elements are marked in blue color. If elements are in reversed order, swap them. So 32 is less than 46 and there are no more elements to compare with, we can move to the next element. 8 is less than 39, so they move to the next element. Now 45 is greater than 15, so we swap them and change the color that the end of array would be marked in red color. Repeat the same steps till the end of given array. With a gap equal to 4, it is not clear how this algorithm works, so let's move on to the next step and reduce gap value, dividing it by 2. Now the gap is equal to 2. We still mark the end of sorted part in red color. In first two steps, only 2 elements are compared, while in third step, 46 can be compared with 2 elements with a gap equal to 2. You can imagine that you are applying insertion sort by ignoring elements that are in the gap. This time elements are in the right order, so no changes are needed. Next step is the same. Moving on, more and more elements become blue. Now 46 is greater than 45, so swap is needed. Then 32 is compared with 45 and they are in the right order, so we can move to the next step. At the end of iteration, all elements are sorted with a gap equal to 2. In the last iteration, the gap is equal to 1. That means that we sort elements like in the insertion sort, marking every inserted element to be sorted, green color. Shell sort has the best time complexity of all sorting algorithms we discussed so far, and space complexity is still constant. However, sorting with a gap may change the order of similar elements, and the algorithm is not stable. Even though this algorithm looks more complex, the implementation is still simple. In every outer loop, we define the gap value, dividing it by 2 until it is equal to 1. Now, in the inner loop, we move with the gap. As it was in the insertion sort, we find the right position for our element, that is the first one in the unsorted part, and insert it. While searching this position, we move elements to the right with a gap. In the next lecture, I will introduce more advanced sorting algorithms. Thank you for your attention.